Hello, Carol, can you hear me?
Yes, I
Yeah,
can hear you.
good, good. Okay, let me start here. So as we agreed, we're going to spend some time on the labs today, and then if we have some time, we'll go over one of the chapter based on Scott email to me. That may be chapter 9. We're going to go through that chapter within this sitting today. Okay, so let's go to the lab first, and let me share screen with you. So we have, which lab do you think kind of confusing and you need to have more information? I know for sure counting and culturing bacteria and correlating between the standard plate count and absorbance, maybe this is one lab. We'll go through this definitely. But what
Yeah.
about, what about the other labs, like effect of like some like environmental conditions on microbial growth, like radiation, like temperature, pH, osmolarity of the media, all this kind of thing. Which one you think we need to go through first?
I'm like working on the one that you just said now.
The
So
counting.
yeah, like the pH environmental lab. That's what I'm working on now. But I do have a few questions from the bacterial numbers lab, like the counting.
Yes.
That
Yeah.
one.
Yeah, let me share with you my screen and see exactly, what you have. Yeah, go ahead. Yeah, can you see my screen?
Yes.
Okay, that is the lab that we're going to talk about now. Yeah, go ahead and start your first question for me, please.
Okay. This might be a silly question, but
No question is silly, by the way. Every single question counts. Believe me on that.
Okay.
Yeah.
So question 4.
Yes, let me see here what we have. Question number 4.
Yeah, I don't know if it's like oddly worded or if it's just I'm overthinking it, but I'm not quite sure exactly what you're asking.
So you mean that why do a standard plate count when running turbidity value? Yeah, it's the main idea from this question is when you decide to do like a turbidity value measurement, why it is so important to have a standard plate count first. Let me tell you this. Okay, first of all, when we do counting, there are several ways of doing bacteria counting. Some of them are easy, straightforward, and less time consuming. Some are kind of taking too much time. So standard plate counting takes a lot of time because you need to prepare your culture, you need to establish like serial dilution, you need to grow your bacteria, you need to incubate and wait till they start to grow and show up on the plates, and then you do counting. So maybe it will take roughly 2 days, maybe 3 days, okay? On the other hand, when you do turbidity, that can be done like in a couple of hours. So this is a main difference between the two. So this is considered to be an advantage of doing turbidity versus standard plate count, okay?
Okay, so time-wise.
Time-wise is much better. So now, why, if I give you a culture of, say, E. coli, and I said I need from you to tell me how much colony forming unit per mil in this culture, okay? So if I'm doing this routinely, like every couple of days you come with an E. coli culture under the same condition and ask me the same question, I need from you to tell me the number. So it doesn't make sense to run every time to do standard plate and do turbidity. It doesn't make sense. So usually I do first standard plate count for the culture to get how much colony forming unit per mil, okay? And then I will establish this value. Now, I know for sure that E. coli at this specific environmental condition and this specific growth condition, they give me this number. So it will be easy for me to take an aliquot from the culture and do spectrophotometer and measure it. But it is very important to establish first a standard plate count for the culture before I do turbidity value.
Okay.
And again, there is another question. I cannot depend on one standard plate count for all bacteria. So I can't use a standard plate count for E. coli to measure the turbidity of Staphylococcus, for example, or Bacillus, because every single organism has its own growth condition and all its own growth, like rate. So I can't correlate those together.
Okay.
The turbidity will be with the specific standard plate count for that particular organism.
Okay. All right. That helps
Okay.
a lot.
So this is
Alright.
what, yeah. And then let me tell you how to do this kind of, first of all, standard plate count. Because I know that there's some, I received already some homework and they have, I believe, they haven't done it right. When you do standard plate, okay, let me see here what I can do. So the first thing you need to go, so I give you a culture, say an E. coli, and ask you, okay, go ahead and do standard plate and tell me exactly how many colony forming unit or SFU per mil. So you need to do, first of all, you can't take directly from the original culture and do plating. You cannot do that. You need to establish a dilution, okay? Because you never know how many. Maybe it will be too much. If you take a little bit of this, will cover your plate significantly. Or maybe the growth rate is very few and whatever you are going to take directly, it will be nothing. So you need to do standard like dilution. In this figure here, we basically take the culture and we transfer 1 ml from the culture to like a bottle, as you can see, with 99 ml, okay, of buffer or saline solution or something like that. So now what I need from you to know is, you need to know the dilution factor here. Dilution factor will be the amount transferred, which is 1 ml, divided by the total volume. So the total volume now is going to be 100 ml, not 99, because I transferred 1 ml to the bottle and the total volume started now is 100, okay? So it will be amount transferred divided by the total volume, which is 1 to 100 or 10 to the power of minus 2. This is the first dilution, okay? Then if I take from this dilution 1 ml and transfer it here, okay? So again, the dilution of this is going to be the same, 10 to the minus 9, but there is something called total dilution, and the total dilution will be, you multiply this much, 10 to the power of minus 2 times 10 to the power of minus 2 for the other bottle. That will be your total dilution here, okay? So this is the total dilution. And then again, if you transfer 1 ml to the next bottle, so the total dilution will be 10 to the minus 6 and so on. This is very, very important to know this, okay? As soon as you have your dilutions already made, now it is time to take aliquots and do plating. When we do this, we have 2 plates for each dilution, okay? And we take different amount. So 1 plate we are going to transfer 1 ml, and 1 plate we are going to transfer 0.1 ml. Okay, and we'll do this and incubate and then look for growth. Before I move to the next slide, now you know what is the difference between a dilution on a dilution factor and the total dilution. So total dilution will be the dilution factor of each of those dilutions. Okay. So the dilution factor for this bottle, for example, is 10 to the minus 2, but the total dilution is going to be 10 to the minus 8. And this is what you worry about here.
Okay.
You do calculation, you use this total dilution here. Okay?
Yes.
So now when you do your calculation is basically I give you an example here. Say this is your plate triptych soy agar before incubation, where you did nothing, and then we have several plates. We have 3 plates here, and those 3 plates came from different dilution. So this plate represent 10 to the minus 4, that plate represent 10 to the minus 6, and that one represent 10 to the minus 8 dilution. And those are how much aliquot you take for plating, 1 mil in each plate, okay? So, and that is your results. Your results is basically, I don't need for me to do any counting here. I gave you like the approximate number, told you like you have here 450 colony, in this plate you got 280, in this plate you got 25 colony. And as you can see, with more dilution, you get less colony. Okay, so now which one of those I need to select when I do my colony forming unit? I need to select a plate which is basically between 30-50 colony till to 300. This is the one that you can count easy, not very crowded, not very diluted, and that will be the most accurate plate to depend on.
Okay.
So you use the equation, which is very easy, simple, which is colony forming unit per mil equivalent to number of colonies you're measuring divided by total dilution of the from where the plate came from and the amount plated. If I'm selecting this plate here, okay, so number of colonies will be 280 and divided by the total dilution for this plate came from the 10 to the minus 6. So I put 10 to the minus 6 here times amount plated. I did plate 1 mil, and you do simple math, you are going to get the colony forming unit per mil.
Okay. Makes sense.
Scott, do you have any question for me?
Yes, I do on that formula.
Yes, sir.
I had 280 divided by 1 10 to the 6.
You have
times
280 divided by what?
10 divided by 10 to the, 1 divided by 10 to the 6. I think that equals minus 10 to the minus 6.
Yes, your total dilution is 10 to the minus 6, yes.
And then is the next number, is it times 1 divided by 10 or times 1?
Yeah, let me do it for you here. Let me do.
Because I got 2.8 times 10 to the 8.
Yeah, let me do the thing here. Let me do something very quickly. Let me do this.
So I'm not sure on the 1 mil if I'm doing times 1 or times 1 over 10.
Okay, so let me go see. So you have the total number of colony 280. Okay, here's the value you have. This is your number of colony 250, and here when you use the equation, this will be divided by 10 to the power of minus 6, right? Like this, and then I need to multiply it. The amount plated is going to be 1 mil. Okay. So it will be, if you do this, when you have a division like that, okay, so what is going to happen is that 250, okay, will be 250 times at 10 to the minus 6, I need to change now to be 10 to the power of 6, okay, because now we are multiplying, it is not a division. It will be 250 times 10 to the power of 6, okay, and times 1. That will be 250, okay, and then 1, 2, 3, 1, 2, 3, right? Which is going to be 2 0.5. You convert this to a scientific notation format, that will be 2.5 10 to the power of 8. And that will be your colony forming unit.
Okay, wow.
Okay,
Okay, got
yeah.
it.
So this is what we do basically. So when you divide, remember you are dividing 250 divided by this. When you multiply now, that need to be changed. The sign here is going to be plus, not minus. And that will be your colony forming unit.
Professor, just so you, on the Zoom, there's a whiteboard feature you can just draw on there. You don't have to do this.
Oh, you mean where? You know, I'm very new in this Zoom thing, so forgive my ignorance on this. So which one which one you talk about?
There is a whiteboard feature where you can just kind of use the mouse and draw on it.
Oh, okay.
I'm looking for it right now.
Okay, I will, believe me, I will learn. It'll take some time for me till I comprehend it very well.
I'm just trying to make it easier on you.
Yeah, definitely, definitely. Yeah. I really need that, man. I really need that.
Yeah, I'm not sure where it is right now, but
Yeah.
it is on there somewhere. You can just draw.
Yeah, but since I'm here in the PowerPoint, this is why I decided to do it like that. But well, this is the way you calculate the colony forming unit. Okay.
Okay. Got it.
Now, you are going to move to a completely different subject, which is how to measure the absorbance, okay? So now we already have our E. coli culture, and we were able to get the colony forming unit for our E. coli per ml. So the second step will be to get the turbidity for this. So in order to do the turbidity, you are going to use the same E. coli culture that you are studying. And again, you're going to do serial dilution from this. You can't take it directly and measure it. And remember, when we do spectrophotometer, we are measuring absorbance. Remember, in a spectrophotometer, light comes in, and some of this light will be absorbed by any particles, like in the media or the bacteria, and some will be like transmitted. And when you have lots of bacteria, that will give you a lot of absorbance. So always there is a direct correlation between absorbance and turbidity. The more, hello? Yeah, the more the turbidity of the culture, the more absorbance you will get. Okay? Can you see? Who is this? Whose baby is this? Hello?
Sorry, it was mine. I muted.
Okay, let's continue here. So when you have your original culture, basically you do serial dilution. So you have test tubes, and you are going to dilute, say, in you can use distilled water, or you can use tryptic soy broth, whatever you can, whatever will be okay. And remember, when you do turbidity, it is not really important to do this kind of experiment under a septic condition. Meaning contamination here is not going to be a factor, because that will be a very quick process. You are going to make dilution and measure. You don't need to worry about culture contamination, because you are not going to use any of these here to do plating, okay? Only standard plate, you need to have everything under a septic condition. So you transfer your bacteria. Say I have these 4 tubes here. Each one, it has 5 ml of the dilution buffer that I'm using, whatever it is. It is maybe tryptic soy broth, maybe water, whatever, 5 ml each. And then I will, if I transfer 5 ml from the original culture to the first tube, so again, the dilution here in this tube will be the amount transferred, which is 5 ml, divided by the total volume, which is 10 ml. I have 5 ml and I moved 5 ml, so the total volume is 10. So the dilution factor here is going to be 0.5 or half, okay? Then I will move again 5 ml from this one to the second tube. So the total dilution, the dilution factor again will be 0.5, but the total dilution will be 0.5 times 0.5, which is going to be 0.25 or a quarter, and so on. So I do this dilution, and now those tubes are ready to measure the absorbance. So I need to take every one of those and put it in the spectrophotometer and measure the absorbance value. If I ask you here a question quickly, in your opinion, which one of those 4 tubes will give you the maximum absorbance? Which one of those 4 tubes will give you the maximum absorbance? Hello. So I have 4 different tubes, different dilutions, okay? So if you look here, you have, which one of those, let me ask you this. Which one of those has the most bacteria and which one has the least?
The half.
The half have the most, perfect, because this is the most concentrated here. And then the least concentrated will be the one, right? Great,
1/16.
perfect. Now, which one will have the most absorbance value? Remember when I said there is a direct correlation between absorbance and concentration? The more concentrated the material, the more absorbance value you will get.
So half again?
Yes, so that will be the most highest absorbance value will be in this one, and the least absorbance value will be in that one, okay? So when you do this kind of experiment, now you have a table. And remember another very important thing before you do spectrophotometer, that you need to have something called, we call it blank. A blank here meaning a media which has everything except for what I'm measuring. Say I'm measuring bacterial cell, so my blank will be everything else, no bacterial cell. What is the purpose of blank? It is basically very important to use it to zero your spectrophotometer and make sure that anything in what you are measuring, because you're not only measuring bacteria, remember, you have bacteria, you have media, you have some nutrients in the media. So the light is being absorbed by all of those, but you need only to get the amount of light absorbed by the bacteria. So you need to use a blank which has everything similar except for the bacteria. That will give you absorbance, and you will zero this, eliminating it from your equation. So every time you are going to measure, next is going to be only the bacterial cell. Is the function of the blank. So now you can have your dilution, you have the absorbance, and as we mentioned, the more concentrated the culture, the more absorbance you will get. So you can see that the absorbance is decreasing with when you increase the dilution factor. Now you have your absorbance, and you know how many colony forming unit per mil, right? So this is the original culture, will be the original colony forming unit. Now, what will be the colony forming unit in half concentration? It will be, you need to multiply whatever you get times the dilution factor, which is half. And here you are going to multiply again the total colony forming unit times 4, and so on. So now your table is complete. You have absorbance, you have number of bacteria. So it will be very easy to establish this kind of nice curve, which correlate the absorbance with the number of bacteria. And you can see clearly it is a very nice straight line, because the more bacteria you have in solution, the more absorbance you will get. As soon as you will get this one, now you know that this is a standard curve for my E. coli when I grow it in a particular media. So anytime I give you culture bacteria E. coli was grown in the same condition, you don't need to do all this again. You take aliquots, you do absorbance, okay? When you get the absorbance value, it will be easy to plot it and get the number of colony from the curve. This is the main idea of the lab, to establish a growth curve like this. So every time I will give you a culture, by taking a sample from it, you can get me the number of colony forming unit by using the standard figure here, graph. I really like to hear questions, because that is the best thing when you have questions, so it make it easy and will open the door of discussion for everybody.
Okay, I have another question. On Q5,
Yes,
it has what wavelength do you measure absorbance of cell suspension? What color does the wavelength associate with?
yes.
And
So
so,
if you look at your manual, lab manual, you will
uh-huh,
see that when we use the spectrophotometer, we use visible light, but we select a specific wavelength. And the best wavelength to be used to measure bacterial growth is basically around 600 nanometer. This is the wavelength that we are using when we measured
okay, so that,
590 to 600 nanometer, which is, if you look at the visible light spectrum, that is very close, you know, to the around orange, kind of orange color.
And
okay.
Professor,
Yes.
I have the same question as Carol because I searched for it through the literature and I could not find it. So I just went online
Yeah, but
and
the lab manual,
yeah,
did you look at
I
the lab?
did.
Oh, it is
I
not
did.
written in the lab
And if
manual?
I
No,
just missed it, and I think several other people had the same question, but I found the answer online and I did come up with 600 nanometers.
Yes,
And then
yes,
it did state that it's associated with yellow. So
yes. It's kind
600
of
between
orangish, yellowish color, yes. If you look at
six
the, I don't know, I don't have,
600 to 570 nanometers.
yes, yes. But I thought it should be in the manual because I remember when we did this lab, it was in the protocol, you know, how we adjust the pH, the spectrophotometer, what wavelength we need to select. I'm positive. It
Maybe it
should
was
be
there,
there.
but I missed it. Yeah.
Yeah, but yeah, I will make sure it is there. Otherwise, I will like send a quick note about, you know, the how to answer this one. Yes.
it does mention six. I like remember the 600 nanometers. I just think like when we're looking, going through the information compared to the question, it's not an obvious like that's what the question is looking for. I guess you could say. You know what I mean? Like I couldn't
Yeah,
correlate those together at all.
yeah.
But
So yeah, yeah. You know, not everything is perfect, as you know. You know,
oh no,
you need to work
no.
for to get it.
Definitely. I mean,
Yeah.
ordinarily we'd probably be in an actual lab rather than
Exactly. And this
going
is
with
what I mentioned last
devices.
time. Remember, I said when you talk about biology or microbiology, you know, you really need to do this everything like in practical, not on like online like that. Yeah. But this is a
Yeah.
situation, yeah, we have to you know go through. But this is the main idea of this lab here. Okay. This is the main idea of that lab. Did not written here. But you need always remember you need to know those facts about the spectrophotometer, that when you use a spectrophotometer, you use light spectrum as your source, but you have what we call a monochromator. And a monochromator, like a prism, its function is basically to differentiate the light, the visible light, into waves. And then you have a selector for a specific wavelength that you are going to use. And this is, you are not using the whole light source or light coming from the light source for measurement. You are using or selecting a specific wavelength to do your experiment. And the other thing that you need to know about spectrophotometer, always remember to use a blank before do any experiment, because that blank is going to make it is made of the same kind of ingredients like what you are going to measure, except for what you are looking for, what you are looking to measure. I'm measuring bacteria, so my blank will have no bacteria. It will have everything else. So that will be like my background that I need to eliminate from the measurements. So I need to make sure that I'm measuring only bacteria. I'm not measuring anything else, because you have materials that will be absorbing light. You don't need those. You don't need those to interfere with what you are looking for. And
Okay.
more absorbance is basically when you have more turbidity. So more turbidity in your culture, more growth, more absorbance value. And absolutely, this is very, very important how to measure colony forming unit, because I will give you in your practical a plate, and I will give you the plate has a specific number, and I will tell you the dilution from where it comes from, like exactly like that. And I will tell you also how much I use to plate. So I will give you all the information. You need just to put it in your equation and do your math.
Okay.
And that will be when we do phage measurements also, Blake, for viruses, it will be exactly the same equation. And instead of colony forming unit, it will be P like a plaque forming unit. This is what when we measure virus concentration. But it will be the same equation exactly. And instead of counting colony, you are going to see clear area on the agar. We call those plaque because this is where bacteria used to be, but it was already gone, lysed by the phage that I'm using. But it will be same principle exactly.
And when you on the question for this lab, you ask about, let's see, question 6. What is the blank used for, and what is the blank made of? Seeing as both of these experiments uses blanks, are you referring to the spectrophotometer
Yes.
for this blank? Okay, just making sure.
When I do the word blank here, it is mainly for a spectrophotometer. I don't use any blank for anything else. When I do standard plating, I don't use blank, no blank. It's only associated with the spectrophotometer, yes.
Gotcha. Okay.
And when I say what is your blank made of, remember, what do you think? If I'm taking a culture like this, I'm trying to measure absorbance, but I need to use a blank. So what will my blank will be made of, in your opinion?
Anything without bacteria?
Yeah, like what?
A buffer.
What else?
Buffer and a detergent.
What else? No detergent. Why detergent? What else will make it more accurate measurements, in your opinion? What if we use tryptic soy broth without bacteria? Can we use that?
Yes.
Because this is basically, it is exactly the same, but no bacteria.
Saline?
Yeah, the saline can be, yes. But remember, when you are using this tryptic soy broth, it's kind of yellowish color due to the bacterial growth. So when you use some of it and you dilute, it will give you some degree of yellowish color. So you need to have your blank also have the same kind of color. So you don't need to have something different. Saline will be like white, clear, clear. That one will be kind of yellowish a little bit due to the media. So it's better to use from the media without any growth as your blank.
Okay.
Yeah. Okay. Anything else for this lab?
Nope.
Okay. So yeah.
Can we go over the first one, dilution? There was only one question on it.
Yes.
But it had kind of multiple parts.
Let me see. Remind me. So you said it's a dilution lab. The dilution problem.
No.
Okay, are you talking about this one?
Yes.
Okay, so here, if you look at this figure here, so basically what you see, you have your culture. You have a flask with your culture. And then again, the first step you are going to do is basically to make dilution So you have here, you are going to transfer each tube. Basically, you can tell that it has 9 ml broth in each one. So you are transferring 1 ml from your culture to your first tube. So now your first dilution will be 1/10, right? 10 to the minus 1, because you have 1 ml transferred divided by total volume, and the total volume here is going to be 10 because you have 9 plus 1. So that will be 1/10 or 10 to the negative 1. And then if you move 1 ml to the second tube, again, the dilution in this tube will be 10 to the minus 1, but the total dilution now is going to be 10 to the minus 2 because you are multiplying the dilution factor. So on. So you are preparing, say, up to 10 to the minus 6 dilution here. Now it's time to do plating. So here in the figure, I already select to have 1 ml sample, not 0.1 ml, only 1 ml sample. So you're going to take 1 ml from each tube in each of these Triptych soy agar plate. Okay? So you are going to expect that the highest dilution will have nothing, and the lowest dilution will basically have lots of bacteria, right? And you are going to see less when you go further in dilution. So you have a plate with 159, you have a plate with 17, 2, and 0. So as I mentioned, the ideal plate for selection will be between 30, 50 colony forming unit all the way to 300 colony forming unit. So definitely I will select that plate here, which is 159 colony. So now I know the number of colony. I know the dilution from where this plate came from. It came from 10 to the minus 3 dilution. And I know the amount plated, which is 1 ml. So it will be, again, a very simple math. Colony forming unit will be the number of colonies, 159, divided by the dilution, total dilution, which is 10 to the minus 3, times 1, which is the amount plated. Okay, then it will be easy math. You can get the number of colony forming unit per ml.
Yeah, I think, so I had everything that you spoke of. My question was the amount used to
Yeah,
make
here.
the pour plate. I put 0.1 mil instead of 1 mil.
Why?
So I don't know, because I was
Yeah.
looking at the previous examples, and that's all I could kind of figure out.
Yeah, here, if you look at this
So-
one carefully, you can see it here, you know, plate
Yeah.
1 ml sample, yes.
Yeah, no, I see that now. And then,
Yes.
so I did, yeah, I came up with 1.59 times 10 to the 6.
Yeah, it should be 10 to the 5.
10 to the 5?
Yeah, because you are going, not 0.1 mil.
1, 2, 3, 4, 5, 6. Huh, okay.
Let me see, let me do them very quickly. But if you divide 1, okay, it will be, let me do this, okay? Here, it will be 159 again. It is the number of colony, 159, and you need to divide by 10 to the negative 3 and times 1, okay? So 10 to the negative 3 times 1, if you look at this, so the second step will be, it will be 159 times 10 to the power of 3 now, okay? Because now you change the sign, and that will be
Yeah, you're right, because
yeah.
I did it, multiplied it by 10. I don't know
Yeah.
why.
Yeah, so it
So
will
it's 10 to
be,
the 5.
yeah, 1, 2, 3, okay?
So it's 159,000.
Yes, so it will be
Got it.
1.59 times 10, and then you count 2, 4, 5.
Yep, I was just using the wrong
Yeah,
pour plate. Okay,
it
got
is, as I mentioned, it is, as soon as you know those important factor about the dilution factor, the plate that you are going to select, amount plated, that will be easy. You can get it easy, you know.
Mm-hmm.
Yeah.
Okay.
It is not hard at all, and believe me, this is, you will see this in your practical for sure. Okay, anything else on this lab?
Not on that one.
Effect of temperature, and I think it was a very straightforward. The thing that I need to focus on when you say effect of temperature, you need to know important thing about when you divide bacteria, and based on the optimum temperature needed for growth, you can divide bacteria into like 4 major groups, and those are psychrophilic, mesophilic, thermophilic, and hyperthermophilic. And those psychrophilic, those like to live in cold condition, like roughly maybe from 0 degrees Celsius all the way to 15 degrees. This is their optimum growth. Mesophil, those most of the bacteria that we know, or most of the microorganisms we know around us, are under this group, mesophilic. They grow well from maybe 25 degrees Celsius all the way to 45 degrees. This is their optimum growth condition. Thermophil, those bacteria that can grow above like 50, 55, 60 degree. They like to grow in this kind of temperature. And then the hyperthermophil, those are crazy kind of microorganism. They love very high temperature. You can say maybe 80, 90 degrees Celsius, very close to boiling point of the water temperature. So this is one way, one thing you need to know about the classification based on the heat requirement, or what kind of temperature they grow at. Okay, and very, very easy. When you have, say, tryptic soy broth like that, you have 4 tubes. This is your control, and you have different kind of growth. When you look at this, you need to look at the turbidity. Turbidity meaning how turbid the culture is. The more turbid the culture, the more growth is in that culture. Okay, this is very, very important. The experiment in the lab was basically to compare between E. coli and Bacillus species, say Bacillus subtilis. Those Bacillus spore former meaning that under unfavorable environmental condition, those bacteria, they have the tendency to form spores. And those spores basically are like dormant. They are not doing anything. They are just dormant, and they can stay there in this kind of environment for many, many years. Say the bacteria, all of a sudden was growing nicely and happy, and all of a sudden, there was like a rush of very lots of acids in the media, in the soil. This is unfavorable for the bacteria. So they are going to respond to this kind of environmental difference by making spores. That spore will stay in this kind of acidic condition for years without being affected. And then as soon as the media or the environment start to improve, acidity start to decrease a little bit, then the spore will germinate and produce what we call vegetative cell. So you expect, if you compare E. coli with Bacillus subtilis, which is spore former, that spore former can tolerate high temperature. So if you have like a suspension from E. coli and Bacillus spore suspension, and you expose it to 3 different kinds of temperature, as you can see here, 50 degrees Celsius, 70, and 100, for few minutes. And after that, you take aliquots and plate on a tryptic soy agar. So for E. coli, you will see them, they can tolerate 50. 50, they can tolerate it, but they hate it. They don't like it, but they can survive this high temperature. As soon as the temperature goes to 70, they are going to die. And definitely 100 they will be completely out. Spore former, on the other hand, they can tolerate up to 100 degrees Celsius. And this is why when we do sterilization, we use like high pressure, because just boiling is not enough, especially if you are dealing with spore former. They can tolerate this kind of condition. Spore can tolerate boiling temperature. So what you need to do in order to kill spores, to do sterilization, and sterilization meaning eradication, complete removal. And you need to apply pressure, high pressure, because that high pressure will increase the temperature. So the temperature of water can reach up to 120 degrees Celsius. You know, under normal condition, that will be vapor and will be completely out. But you are making steam, high temperature, and under this condition, the spore will die, will not tolerate this. Okay. So question here was kind of straightforward. I can't see any thing unless you need to know what is a thermodiuric mean. What is the difference between a thermophil and thermodiuric? Any idea?
Thermophilic can withstand temperatures between 41 and 122 degrees Celsius.
What
So
about
they're-
what is the difference between, okay, we know thermo means temperature. What is the difference between philic or phil and diuric? The suffix here is very important to know. The
Liquid?
difference between philic and diuric.
I don't know.
Yeah, philic, living, loving. Always anything that is like hydrophilic. Remember, hydrophobic, meaning it is a condition of loving specific condition. So when you say hydrophilic, this is basically solutions which like to be like polar. They like to have this kind of condition. They like water. They like to be in a water environment because water, as you know, is polar. Okay, and hydrophobic, on the other hand, they hate phobia. Phobic, phobia. They hate anything that has water. Water is polar and they are non-polar, so they can't mix. Here, diuric tolerant, it can tolerate, but they don't love it. So if you have a bacteria that basically, if you have a bacteria, say 60 degrees Celsius, thermophilic will love to grow, even they need this kind of high temperature to thrive and increase in number. Diuric, on the other hand, they can tolerate it. They don't like it, but they are in a situation that they need to live with it. Okay, they need to be tolerant, but they prefer a lower temperature. Is the difference between diuric and thermophilic. Like for example, when we do like pasteurization, we apply high heat for a very short time. Some of the bacteria is basically thermodiuric, meaning that they are going to tolerate this high temperature. This is why when you look at any pasteurization product, you'll see specific due date. It means that after the due date, the number of those thermodiuric will increase to the point that they are going to spoil the food. So you have to eat or drink this food before the due date. Because before the due date, there is a limited number of those there. It doesn't mean that the milk that you are drinking is sterilized. No, it is pasteurized. Pasteurization meaning trying to eliminate, especially those like pathogenic bacteria, not eradicating. Eradicating meaning removal completely. You can't sterilize milk because when you do that, you are going to denature the protein of the milk. You are going to make cheese, not really milk. Okay, so you need to expose the milk to a high temperature, very high temperature for a very, very short time to kill any kind of pathogen. But there's some bacteria that is going to tolerate this. We call those thermodiuric. Okay, it's important. Same deal for halophilic and halodiuric. Halophilic meaning they love salty condition. If you grow those kind of bacteria in the lab, they need maybe 10% salt. If you decrease the concentration of salt, they are not going to grow. Those are halophilic. They really like salt to be active and physiologically to be active. Halodiuric, like Staphylococcus, for example, they basically can't tolerate high salt. They are in your skin, a sweat gland, which is basically producing lots of salt, but they're still there. They don't like it, but they can tolerate it. This is what we call halodiuric.
Professor, I do have a question.
Yes.
On question 1, it says which test tube shows maximum growth and which one shows minimal. So there are 2 C's in the illustration. So
It's a good plan. Yeah, that C is control.
okay, so I don't use that as one of the answers because that would be the minimal growth, but that's
No,
the
that is a
control.
control here, meaning that you didn't put any kind of bacteria at all. That is your
Okay.
broth. But that's a good point. That's
Okay.
very confusing. A, B, C, that should be like a control and then different culture,
And then on
should
the
be like,
second question, on the thermophile, on the hypothermophile, if I look at the effects of temperature on microbial growth chart that's in the lab, thermophile's optimum growth is about almost 70, between 60 and 70,
yes,
and hypothermophiles are between 90 and 95, it looks like, or 90 and
yes,
100.
yes,
Now, we don't have that option on this
yes,
chart, so I just
yes.
put them into the 45.
No, no. When you look at this, you need to put not applicable.
Oh,
Because
okay.
this is the main idea of this question. It gives you 5 different temperature, and the maximum here is 45, and definitely the thermophilic and hyperthermophilic, they cannot do anything here. Okay, so you either put like not applicable because there's no temperature enough for those.
Okay.
Yeah.
Okay, good. I didn't have the option there, so I didn't know what to put.
Yeah, because it said use a plus sign to denote growth. For thermophilic and hyperthermophilic, those like high temperature, so they will grow very, very minimally, if any, at this. Because they're really philic. They really like and love high temperature. You know what I mean? If it is thermodynamic, yes, but no. Yeah, here you say not applicable.
And then I do have a question on the third Q3. It says record the results of the extreme temperature exercise. And I can't for the life of me figure out what that means or where I find that information. Because it looks like you almost have to do the experiment to get the
Remember
results.
this experiment? So here is an experiment that you were talking about. So you have E. coli, you have Bacillus spore, and you have 3 different kind of temperature, as you can tell. So you can, if you look at E. coli, you can see clearly E. coli grow up to 50. Okay, but at 70 and 100 is nothing. So basically, if you go to the chart here, so 50 you can do plus, okay, and then 70 is going to be minus, 100 is minus. Bacillus is going to be plus, plus, plus for everyone. Okay, now it says here add more pluses, not just a plus. Okay, so if you compare E. coli and Bacillus spore at 50 degree, what do you think? E. coli can tolerate this temperature. Bacillus spore love this kind of temperature because they can tolerate it for sure. So if you put pluses, in your opinion, are you going to put more in E. coli or more in Bacillus?
Bacillus.
Yes, so here, if I put +1, okay, here I can put +3.
Yeah.
You know what I mean? Here I put minus because I can see any growth at 70. And instead of putting +3, I may put +2 because they are not thermophilic. Bacillus is not thermophilic, Bacillus subtilis, or the one that we're using in the lab. They can tolerate this high temperature, okay?
Okay. Yeah, and that's all I had for that. I'm not sure about everybody else.
Okay. You have any question? Anybody had any question for me, guys?
Well, could we go to the, I think the last lab of the 4, which is environmental condition and bacterial growth?
Yes, let me do this. Let me first, I need to yeah, you're talking about this one, right? the effect of pH, effect of UV light,
Yes.
and effect of salt?
Yes.
Yes. Again, here, those are other environmental conditions that can affect the growth rate of any bacteria. And if you look clearly here, based on pH and how bacteria can grow in different pH, again, those can be divided into three major groups. Those called neutrophil, and neutrophil meaning that they grow the best around neutral pH, between 6 and 8. Acidophil, on the other hand, they prefer acidity condition, okay, to grow. And remember, again, there is an acidophil and there is acidotolerant. And again, here the main difference, acidophils, they like low pH to grow. They need it. If you grow those acidophil, you need to make sure when you prepare the media to have a buffer that lower the pH of the media. Otherwise, they are not going to grow optimally. Acidotolerance, on the other hand, they can, they don't like low pH, but they can tolerate it. And this is an example, very, very classic example here about Helicobacter pylori. This is some people, they have this kind of bacteria in their stomach. And this is the main cause for gastric ulcers in people. And you know how acidic, high pH, how low pH in the stomach is. But they can tolerate this. It doesn't mean that they need low pH to grow, but they can tolerate it. Lactobacillus, also the same thing. They make yogurt and they can ferment lactose and make lactic acid. So they lower the acidity of the media, but they can tolerate it. They can live with it. But you can grow them in neutral media, in a neutral pH. So this is one thing that you need to know from this lab. And also you need to know about the radiation. It is important, and this is covered very thoroughly in chapter 9. That when you talk about radiation, you can divide radiation into ionizing and non-ionizing. Ionizing, those are very tough. Those are basically cause an electron to leave the atom, creating ions. Very high power, like gamma and X-rays, for example. Non-ionizing, they just destroy, like some bonding, like hydrogen bonding, but without creating ions, like UV light. And this is the one that we use in the lab to see the effect of UV on growth, okay? And this slide here show you the different time of exposure, okay? Our culture was E. coli, and it was exposed to UV light for different time period, okay? 10 seconds, 60 seconds, 5 minutes, okay? And this is 60 seconds with lead. Now, my question is, by looking at those three here, A, B, or A, B, and D, what the time needed, which one described that, the best time to eradicate and or to remove or to kill bacteria?
D.
Very clear. You have little bit, but it's not 100% removal. You still have some colonies. But if you compare it with 10 seconds, you can see the big, huge difference. So now, what does this experiment tells you? If you expose, why when you expose for 60 seconds, you have here some bacteria, and when you again expose with 60 seconds, what is the main difference between these two here?
Airborne contagions.
The lid.
Yes, the lead. The lead will tell you that the UV cannot penetrate too much. This is why if you have UV exposure without a cover, it is more efficient than if you have it covered. So covered here, that lead prevent lots of UV from coming in. This is why UV is not non-ionizing. UV is weak. So you need to be in a direct contact, no barrier. If you have a barrier, even like a lead like that, that will make it weaker, and that make, bacteria will grow without any problem. Okay.
Professor, so on one of the questions on question 2, it says, which UV exposure could result in a good antimicrobial efficacy based on the test results.
Yes.
I put actually 10 because that eradicated all the
Yes. Yes.
bacteria
Absolutely yes.
completely. But
Yeah.
the example we just talked through, I just wanted to make sure that I wasn't missing
Yeah.
something. Okay.
If you look at 5 minutes or less, you still have, see, some bacteria. See, look at 10 minutes, you have that plate, part of it was covered,
Yes.
and the other one was left exposed to UV, and you can see the difference, nothing here. So yes, absolutely, the answer for this question will be more than 10 minutes will be the best, yes. And here, yes.
Answering these real quick, we can just put like A, B, C, or D, like the question, and then just like A, B, C, or D, right? We don't have to like explain.
No, no
why we-
explanation,
okay.
no. I did
Okay.
not, if I say why, then you need to explain.
Okay,
But this is a very simple multiple choice.
right.
And then on question 6, Professor, says which organism is likely the Staphylococcus aureus based on the results shown on the picture? I put B because it is able to survive in high salt content, whereas A died.
Okay, here, if you look at it, you can see, first of all, you have 3 plates with different salt concentration. You have 0.5, you have 5%, you have 10%, and you have 3 different kind of microorganisms, A, B, and C, okay? And if you look at them, you can see at 5%, till 5%, all 3 can grow. And then at 10%, so you have A cannot, but you have B and C, you can see some growth. So which organism is likely a Staphylococcus aureus based on the result? We know that Staphylococcus aureus, and this is when we do the lab for staph identification, I think in the 2nd semester, you will see that Staphylococcus aureus are basically halodurants, meaning they can tolerate high salt. So the right answer for this is going to be B and C. So if you compare A and B, definitely it will be, because here, you know, 5%, 10%, okay? So they still can grow at 10%. And we know that they are halodurants, so they can grow at high salt.
And how do we distinguish, or on question 5, it says organism C is, how do we distinguish whether it's
Yeah, what
solid?
do you think when you have, yeah, you said, is it going to be non-halogenic or halogenic or halophilic? How to distinguish between those 3? First of all, A is going to be omitted completely because it is halodurant. Okay, it can grow at this kind of salt, right? Now, you need to compare between B and C. When you say halophilic, it means they can grow best at this kind of. In other words, you will never be able to see a halophilic bacteria that grow at 0.5% or 5%. Okay? You know what I mean? Halophilic, they need salt in the media. So if you have an halophilic bacteria and you try to grow in 0.5 salt, you will have 0 growth. 5%, you will have 0 growth. You will start seeing growth 10% and more. So to answer your question, that's going to be halogenic. If they are not growing here, then I will say they are halophilic. You know what I mean? So again, this is the main difference between halogenic and halophilic. Halophilic, they love salt in the media to grow. It is needed. It is necessary element. If you remove it, they will not grow. In this 0.5 salt, this is nothing, very less salt. If they really love salt, they will not grow in this condition. You know, they need high salt to grow. So we can consider them halophilic. Only will consider them halophilic if there is no growth at 0.5, no growth at 5%, and they start to grow up at, to show up at 10. Got that one?
Yes, thank you.
It's very important to know the difference between halophil and halogenic.
Yeah, I saw the definitions on the slide, but I just couldn't tell from the picture and
Yeah, whether they are halophilic or yeah. So halophil, they love salt, high concentration of salt. So zero point 0.5 for them is nothing. They will not grow. I got the chance, to isolate some bacteria from the Pacific Ocean for oil degradation, like many years ago, and they grow only at media with 15% salt. If I have 10% or less, they can grow. Those are real halophilic. Okay, so I believe, unless you have any question for me, because I need to finish, I have another meeting in 30 minutes. So do you have any question for me? I was planning, as a matter of fact, to go through some of the lecture as Scott suggested, but we're going to do this on Monday.
No, thank you, Professor. So helpful to be able to
No problem.
talk through
My
this.
pleasure to talk
Yeah.
to you guys. And
And
I will post a link for this recording for sure.
and do you like the approach of so Fridays in the afternoon like this, and then on Monday,
Around 5? Around
Yeah.
5? Yeah.
Whatever works, because honestly, I only had maybe a handful of responses from the class, so I didn't
Most
really
of
get
the,
it.
I believe most of the students, they prefer to have like a link for recording so they can look at it at their convenience, Some of them are working, some of them are traveling, so it's different. So I believe, recording the meeting will be very, very helpful for those students,
And
That's,
this is just me, but I am working as well, and but 5 o'clock will be a little bit difficult for me because I'm but
oh, you mean I can shift? For me, I'm
and
fine. Monday, I'm okay.
if
Like
it's
7?
six or so, I could do it, but I could be on live. But if it was 5, I would just have to listen to the
Okay, I
recording.
will shift it to 7. What about that?
Okay, yeah, that'd be great.
And again, recording it. So if
Yeah,
some student will not be able to attend, so they can see the recording.
I would just prefer to be able to ask questions live. So,
I,
but I get it.
yes, and I also prefer if you guys send me ahead of time some of the questions, so we'll make it more like efficient in terms of the timing, so we can, instead of going through everything,
Yeah.
if I received like maybe 3 questions for unit 1, maybe 2 questions for unit 3, maybe 7 questions for unit 10, so this way we can cover many units at the same time. You know what I mean?
Yeah,
I don't know if I missed it, but did you guys go over that last section? I think it was with the charts, with the, I'm not even looking at I think it was the last section.
Which one again, say?
Hold on, I'm looking for
effective
it.
temperature.
Yeah.
Yeah, that's so. He did go over that.
Yeah, it was recorded, so I will send you the link. I will put the link so you can see that one.
Okay, yeah, I'll go over it when I have time.
Yeah.
And
Okay.
Professor, just
Yeah.
to, I was just curious when you were talking about endospores.
Yes.
I looked up what's the oldest known endospore
Yes.
out there, and what came back was a 9,000-year-old
Yeah.
endospore.
Yeah, they were able to isolate, I believe, some endospore former from a mummy,
Yeah.
Yeah, yes.
Okay.
By the way, before I conclude this meeting, I spent like almost 15 years working with a bacteria, we call it Bacillus thuringiensis, and it is a spore former. And the unique thing about this bacteria, it is entomopathogenic, meaning it is very efficient in killing different kind of insects. So they can kill different orders, Lepidopteran, Dipteran, mosquitoes, house flies, caterpillar, beetles, nematodes. They are very, very specific, and they have lots of toxins, as a matter of fact, which is very specific for insects, being used for many, many years, like tens of years, for just topical application on plants to protect plant from insect. And we started like 15, 20 years ago to try very much to get the genes out from those bacteria and put it in plants like cotton, like corn, some vegetables, to create genetically modified crops that can tolerate and resist insect damage because those transgenic plants. I did lots of work with this group of bacteria. We were able also to identify receptors from different kinds of insects that recognize those toxins. So I enjoyed working with this bacteria. It is very fun to work with. But as I mentioned, if you have a contamination with another spore former, it will be painful, very painful to be able to isolate those from each other. So it is very, very critical, but fun to work with.
Mhm.
Yeah. Okay, guys, I enjoyed having meeting with you, and I'm going to go see you again on Mondays.
Thank you.
Thank you very, very much. You have a wonderful rest of the day.
Thank you. You as well.
Okay. Bye, 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 bye.